Okay. So like I said it is what? It is a 4 plus 2 pi cycle addition of conjugated diene, which gives us the 4 pi, and a dienophile, which brings the 2 pi, to yield or produce a substituted derivative of cyclohexane. Let's look at the typical example. We know what conjugated diene is, Nabi?
Yes.
Something like this. Double, single, double. That's a conjugated diene. Now react with something like this. This could be a dienophile. Dienophile could also be something like this. It could have any derivative at all, but this is what I'm talking about. So when I say a 4 cycle addition, it means this cyclocarbon, this carbon, this carbon, this carbon. They all have pi electrons. 1, 2, 3, 4. So because they have pi electrons, we say it's donating 4 pi. And then this one, there's pi electron, so that's 2 pi. So the 4 of this one and the 2 of this one are going to combine together. How is that going to happen? First of all, the first pi of this one will attach itself to this carbon. This pi carbon here will attach itself to this pi carbon. But now that it has attached itself to this pi carbon, this guy is having an excess. So it has to push its own pi electron down to this side. And when that happens, this carbon now has an excess. So this carbon here has to now push its own down to that guy, causing them to form something like this. Causing them to form that. So that is the whole point of what's it called? Diel-Alder reaction. Is that clear? It's not clear. How is that not clear? What's hard in this thing that I just explained now? This carbon has pi electron. It gives its own to this guy. How many bonds can carbon take?
4.
Know that this guy already has something like this attached to it. I mean, now because this guy has donated 1 electron to it, that will cause it to do what? Now have extra. Because he already has 1, 2, 3, 4. You now give him this one again. That's 5 now. So it's in excess. So it has to break this one that is here to this point. When it breaks this one that is here, now there's now another extra bond here. This carbon now, that already has 1, 2, 3, and 4. Because there's hydrogen here. Now has extra 1, which makes it what? 5. It's not possible now. So this one here now has to break its own bond to form with this carbon. So this is the first carbon that is here. The second carbon here is this one. This third carbon here is this one. This carbon here is this one. This one that is bonded to is this one. This one that is up is this one. So how is that not understandable? So this is a diene. And this is a dienophile. Dienophile will always have like an attachment aside from the double bond. They will always have an attachment. It could be an oxygen attachment, it could be cyano attachment, it could be anything at all, but they will always have an extra attached to them. It will not just be double bond. There will always be an extra. Examples of diene. We have 1,3-cyclobutane. We have 2-methyl-1,3-cyclobutane. Then we also have the Sorry, cyclopentabutadiene. And it's pentabutadiene. Cyclopentabutadiene. And we also have cyclohexapentadiene. I should write it. Dienophares are electron releasing group, while dienes are electron withdrawing group. So dienes we call it.
Dienophares are electron.
Dienophares, they are electron releasing group.
What about dienes?
Dienes, they are electron withdrawing group. Look at this one. What happens here is that this carbon here will donate. Then this bond breaks and comes here. And then this bond breaks and donates to this place. So what would it look like? It will look like this. That's it. So this is where the bond will be. All the other bonds will be gone. That's what you have. If you want to see where did all the bonds go, you can even look at it. There was no bond here joining this carbon and this carbon before. Now you have created one by breaking one. There was no bond joining this one and this one before. You created another one by breaking one, that's two. And the third one, you now put it here for you. This will still attack here. And this will attack to here. And then this bond will still break to this point. So you have something like this. Have you guys not seen what do you call it? What do you people call that anyway? The people did 413. Sorry, 313. You people not see bicycle compound. This is bicycle compound.
I don't think I saw something like
This is what you have.
yes.
The same way, yes. But you're going to be attacking from both ends. The first one is going to attack from the front here, so you have something like this. That's the first one. Then the second one is now the other side. And that's it. So this is twice. You're attacking twice. So he's attacking on this side, also attacking on this side, forming this. So this is the joining part. This is where we joined it together with this guy. Sorry, let's see. So this is Wurtz reaction. Wurtz reaction. is the coupling of haloalkanes. It involves the coupling of haloalkanes with sodium metal. With sodium metal. The coupling of haloalkanes. That's alkyl halides. Haloalkane with sodium metal in dry ether solution. To form a higher alkane. So they form higher alkane. Now this is what happens. Let me show us. I'm going to use another reaction to show so that I will not be looking at RR too much. So let's say we have CH3, CH2Br. This is a haloalkane, I mean. Now this haloalkane will react with sodium. But the thing that happens here is that the splitting of this bond that occurs here is an homolytic splitting. You know what homolytic splitting is? That is that kind of splitting whereby normally it's two electrons that form the bond, but the carbon and the bromine, when they break their bond, this one takes its electron, this one takes its electron, thereby forming free radicals altogether. Naturally, if this bond breaks, because it's bromine is highly electronegative, it would have taken the two electrons. But this particular splitting that is occurring here is known as an homolytic splitting, which we regard as what? The formation of free radicals. So a radical will be formed here, which will be bromine radical and a CH3CH2 radical as well. That's what we're supposed to have naturally. So we have CH3CH2 radical. But because sodium is here, if you check, sodium has one electron in the outermost shell. Sodium usually have one electron in the outermost shell. That's why sodium is 11. Abi? Yes. And that's 1s2, 2s2, 2p, 6, 3s1. So they have one electron in the outermost shell. So they are willing to give out that one electron. So it will now give that one electron to bromine, which would now make them Na plus. You know, when it loses electron, it becomes plus. Then bromine is now Br minus. Are we there? So bromine is now Br minus. Now, this radical that is here, this radical, CH3, CH2. Don't forget that in the beginning, look at the beginning of the reaction here. It is two of this and two of this that is reacting. Two of the haloalkane and two of the sodium. So in this place now, the second sodium molecule will now react with this radical. And don't forget, we've already said that this guy is radical. This is a radical and it's on carbon. And carbon is electronegative as well. So what they will do to sodium is that they will pull electron from sodium. So you now have CH3, CH2, then this is now having minus, and it's now bonded to sodium, that is plus. So this guy will now be cited, that is the CH3, CH2, that is minus, Na plus, will now be cited by their CH3, CH2, Br, the initial one. That is the second molecule, since this is two of it. So bromine here now will be attracted to sodium. Because that's the thing. So bromine will be attracted to sodium. And when this bond breaks, this guy will become positively charged. So since this one is positively charged and this one is negatively charged, they automatically now form CH3, CH2, CH2, CH3 plus NaBr. So what's the point of Wurtz reaction? To form a longer chain. That's just it. To form a longer chain. So this is what happens in Wurtz reaction.